Good morning, everyone. This is Mitchell Shaw, and I'll be presenting today on two-way deterministic finite automata. We'll start with the introduction. A two-way deterministic finite automata is an abstract version of a DFA. Key difference between a 2DFA and a DFA is regarding transitions of the input string. In a DFA, given an input, move to the right of that character in the input, which is what we've learned from day one. In a 2DFA, we have a read head, a new component that allows us to move left or right on the input. Two end markers mark both the left and right hand sides and are not included in our alphabet sigma. The read head is not allowed to move outside of these bounds. A 2DFA also only needs a single accept and reject state. Here we'll go over our formal definition of a 2DFA, where M is our machine and our octuple, which is Q, which is a finite set of states, sigma, which is our alphabet, the left and right end marker, these are not included in sigma, theta, which is our transitions. We take into account sigma in the union of the left and right end markers since they're not included in the alphabet, which points us to some transition function that will move our read head left or right. S is an element of our set of states Q, which is our start state. T is an element of our set of states Q, which is our accept state. And R is an element of Q, which is our reject state. And note that R cannot equal T. Some additional constraints in regards to transitions. For all little q is an element of Q, theta Q given L equals Q prime, and it moves to the right. And for some Q prime that is an element of our set of states, and the same follows that given some state and an input, we either move to the left or right and enter a state in our set of states. So you may be wondering, what does this mean given an input string? And input strings here are on a finite tape and are strictly read only. We have one symbol per cell of the tape, and note that the left and right end markers both take up one of those cells. At some given point, the machine is in a state Q, scanning an input symbol or an end marker. So our input string here is just some series of the letter A, which is our sigma. And we have a state Q that is currently on the second A of input. It then moves to the left or right, entering a new state. Here we call Q prime, and we'll just act like given a transition that the read head just moves right at state Q given A. So an example to kind of show us something real. Consider a 2DFA machine that behaves as follows. We start in our state Q naught, and M, our machine, repeats a cycle of moves where the tape head moves right until two ones have been encountered, then left until encountering a 0, at which point state Q naught is re-entered and the cycle is repeated. More precisely, M has 3 states, all of which could be final. Theta is given as follows. So this little table over here to the right just kind of shows you where if we're at this state and we're given an input, where we should go state-wise, and if we need to move our input, our read head on the input right or left. So here we have a little example where Q is a set of states Q naught, Q1, and Q2, and sigma is our alphabet of zeros and ones. Our left and right end markers. Our start state will be Q naught. Our accept state's going to end up being Q1 here, and our reject state's going to end up being Q2 because we don't want to finish at Q2. And we have our thetas up there that has all of our transitions that we've translated from the table. So we'll start at Q naught given the left end marker. We transition then to the right and stay in state Q naught. Then we see a 1, and then given our little transitions we have over there, we see that we need to transition into a new state Q1 and move the read head to the right. We see a 0 then, and stay at state Q naught and move the read head to the right. we see a 1 and transition to a new state Q2 and move the read head to the left. We are now in state Q2 and we see a 0 to the right. Note how we can accept input that we have already seen. We enter a new state Q0 and then move the read head to the right. So we see a 1 now, and then now, given our transition, we can transition to a new state Q1 and move the read head to the right again. We see a 0. This is in our constraints, so we move again to the right and stay in state Q1. And now we see another 0, and we stay in state Q1 and move the read head to the right. Now we see a 1, which means we need to enter a new state being Q2, and we need to head back left. Here we see a 0 and enter a new state, which is our start state Q0, and move the read head to the right. We see a 1 and enter a new state Q1 and move it to the right. And finally, we see our input marker symbol that we're looking for, which is our right in marker, showing that we can accept this input as fulfilling what we need it to. So notice the key things to take away from this are that we can move left and right, and we can also iterate over input that we've already iterated over given our transitional rules. We covered a couple different input symbols multiple times so that we could meet our constraints. Is it a Turing machine? This is the big question, and that is, well, yes and no. You can regard it as a pseudo read-only Turing machine, and it is regarded as such in the academic community. It has a tape and a read head. However, a Turing machine has an infinite tape, and as we coin read head for the 2DFA, tape head is appropriate for a Turing machine because it can read and write to cells. They have no memory. They can use Turing machines, and as input grows more complicated, more memory is needed. So I hope this little presentation helped everyone understand two-way deterministic finite automata a little bit more. And we're going to follow this by a short Q&A, and I hope that everyone will be nice in their questions. You guys have a good one, and Mitchell out.